morning. Today we shall begin a new chapter. This is on solidification of pure metal. Metal is mostly used in its solid state and its structure depends on how it has solidified during the process of solidification. So, we shall look at it in little detail, and under this we will cover the nature of cooling curve. We have already talked about during thermal analysis, and during the process of solidification it will pass through a state when both liquid and solid will be coexisting, and phase rule states defines how many phases or what are the variables which can control this. We will also introduce concept of free energy, entropy and surface energy. They are very important concept to understand the process of solidification. We will also explain why for solidification to proceed some amount of undercooling is necessary, and the process of solidification is a time dependent process. There are two steps and these are called nucleation, when a certain number of very small nuclei of solid will form in the liquid. We will look at it energetics of nucleation, and thereafter nucleation there is a time dependent growth process. Former, this is probabilistic, stochastic in nature, whereas this is a deterministic, it will follow certain growth rules. We will make a distinction between homogeneous and heterogeneous nucleation, what they are, and then we will also look at the constraints which are imposed on liquid metal during solidification and why the solidification proceeds in a particular direction. And this has been used to solve or to get particular desired properties and textures in materials. Now, let us look at the cooling curve of a pure metal. How does it look? So, at a particular temperature above its melting point, it is liquid. Structure of liquid is quite different from that of solid. We have seen that solids are crystalline, atoms in solids they are arranged in a regular or periodic fashion. Solids are incompressible, its bulk modulus is very high. In comparison to this, liquids flow easily, whereas solid it does not flow unless you apply certain stress, it does not flow, whereas liquid will flow of its own, and it can take the shape of the container where you keep. That is not so in case of a solid. This is primarily because the atoms are not as closely packed as in solid. Secondly, the atoms are more mobile and you can say that atoms are arranged in a disordered fashion, but there may be some amount of short range ordering. Using X-ray diffraction technique, the density of packing also has been estimated. So, in case of solid, we have seen that coordination number, that maximum coordination number in metal that you can have is 12 in face centered cubic, whereas same metal which is has a in solid face centered cubic structure, if it gets converted to liquid, possibly you will not have that 12 as the coordination number. Coordination number will be less than 12, but nevertheless still quite high, maybe 10, 11. And when this liquid cools, say it will cool and this plot temperature, it can be a smooth curve like this, and this will be primarily determined by the temperature of the metal and the surrounding, and usually this follows the Newton's laws of cooling, and that is why I have put it like this. And when it reaches freezing point, that is the time, if some amount of solid forms, then the two phases will coexist for certain length of time, liquid and solid, and during the solidification process it will release heat also, and you will find that here for some time that cooling just stops. It maintains a constant temperature until solidification process is complete, and once this is completed, then again the temperature keeps dropping. Now, Gibbs phase rule gives us a simple relationship between the number of phases that can coexist at a given condition, experimental condition, and normally experimental condition we mean, say the temperature is 1 and maybe and the pressure and at which you are doing the experiment, and usually for most practical applications this pressure will be 1 atmosphere. So, you have two control variable, temperature and pressure, and Gibbs phase rule states it is like this: P plus F equal to C plus 2, where P is the number of phases, C is the number of component. Now, in case of a pure metal, the component, that just one metal, so number of component is 1 and F represents degree of freedom. So, basically it is number of control variable that you have. Basically here the control variables are temperature and pressure. Now, in this case, when during the process of freezing you have two phases, liquid and solid, coexisting, in that case number of phases are 2, and then if you substitute here you get degree of freedom is 1, and in fact this 1 degree of freedom means it is the pressure. So, this temperature, freezing point or the melting point, is fixed for any metal, is fixed at a given pressure. If you change pressure, of course, this melting point can change. So, at a constant pressure, liquid and solid can coexist at a fixed temperature. So, this is the outcome, I mean this is the prediction or what Gibbs phase rule states, and this is applicable to even multi-component system. Now, what is a phase diagram? Basically, phase diagram is a graphical representation of the stability of phases in a single or multi-component system at a given state, and a state is defined in terms of control variable, and usually only two of these set out of temperature, pressure and volume, only two you can control. So, and for most practical purposes we can control temperature and pressure. Now, let us look at the how this stability of a single component system depends on pressure and temperature, and this is shown over here. This axis represent pressure, this is temperature, and you can have a pure metal, say it can, you can have three different state: liquid, solid and gas. And this pressure temperature diagram gives us the regime in which the solid, liquid or gas is stable, which is shown here like this. There are three important lines, and these lines represent the equilibrium between solid and gas. There is a possibility the solid can be transformed entirely to gas without going through this liquid route. Similarly, you have this line which represents the line in which represents the equilibrium between solid and liquid, and this line represents the two phase equilibrium between two phases, liquid and gas. And say suppose 1 atmosphere line intersects here. In that case, this is the freezing point of the metal and this is the boiling point of the metal. So, and this particular point is a critical point which represents equilibrium between all three. So, that means under this condition all the three phases solid, liquid and gas can coexist. So, for a particular for this particular case, if you try and apply phase rule, you find for the triple point the degree of freedom is 0. So, for any material, any pure material, say water, this is a fixed point and this is which is written over here, this T naught is equal to almost 0.01 degree centigrade and pressure at that point is 0.006 atmosphere. Now, let me introduce a concept of Gibbs free energy. This if we put an analogy, this is some kind of potential, say like energy, you can or let us say electricity flows from higher potential to lower potential. Similarly, any transformation when it takes place, it will take place in a direction from a higher potential energy to a lower potential energy. And Gibbs free energy, you can say it is an analogy, it is something similar to chemical potential. And we know that from second law of thermodynamics, that although the entire amount of mechanical work can be converted totally to heat, but it is impossible to convert totally the heat into mechanical work. So, that means in a system there is always a part of the energy which is not accessible, which you cannot transform. And Gibbs free energy, it is a thermodynamic parameter. You can say that it determines stability of a phase. Any phase which has a lower free energy will be more stable, and this is defined as G is the Gibbs free energy. It is H means it is molar enthalpy minus T is the temperature in degree Kelvin times a term called entropy. The entropy is a measure of disorder, and if you multiply this entropy by the temperature, this gives a measure of energy which cannot be converted, it is locked. So, whatever is the free energy is G is enthalpy minus T times entropy. And we use this expression primarily whenever there is a reaction taking place at a constant atmosphere. And for most practical experiments or processes, the atmospheric pressure is constant and usually it is 1 atmosphere pressure. There is a differential way of representing this, and this is a simple thermodynamics principle. Say you can convert it and write in differential form, that is dG, and you can convert it in terms of from enthalpy and entropy to pressure and temperature, because these are the easily controllable variable. Then it comes out that dG, incremental increase in free energy, is equal to V plus incremental times incremental pressure minus S dt. Now, let us look at the process of solidification. We are concerned with the stability, relative stability of two phases, one is solid, another is liquid, and if you try, so this is a something, try to plot, this is solid, not entropy here. This line represents the free energy as function of temperature for solid, and this line represents free energy of liquid as function of temperature. Now, let us look at it at high temperature, which has lower free energy, it is liquid. So, higher temperature liquid is more stable and these two lines intersect here. So, this is the freezing point or melting point. Below this solid is more stable because it has lower free energy. So, you can visualize the process of transformation as a chemical reaction like this, liquid to solid, and they can coexist at this freezing point. Both can coexist at the freezing point. At that time, if we can use this expression, you can write two separate expressions, one for liquid, another for solid. And if you equate the two, so essentially what is happening is does solidification begins immediately when it comes below the freezing point. At freezing point this is 0, but what happens when a solid nucleus, a nucleus of a solid forms, a new surface is created, and to create this surface you have to apply certain amount of energy. Where does it come from? What is the driving force? So, that means that energy has to be supplied, and this can come from this chemical potential, and this is possible only if you go down, I mean undercool a bit, you cool it the system to a little lower temperature, then you have the solid has less energy, free energy than the liquid. So, there is a net energy transform, there is a net available energy is there, which is used up in creating new surface. So, for the solidification to proceed, you need some amount of undercooling, and this is shown over here. Actual ideal curve we had initially shown, but here even if you leave it indefinitely at this temperature, solidification will not begin unless you have enough energy to create new surface. That's the surface, that is solid liquid surface is created. So, this is shown over here, and once the solidification begins, that latent heat will raise the temperature back to the freezing point or melting temperature, and here both liquid and solid will coexist until entire amount of liquid is transformed into solid, and thereafter it will follow the normal Newton's law of cooling. Now, we had shown this phase diagram for a pure metal and or a pure material, and let us look at the case of water. It freezes. There are three phases involved: ice, water and vapor. Now, here look at this slope. Is it see, most cases the slope is positive whenever the transformation is associated with increase in volume. Say ice to vapor, liquid water to steam or vapor, it is accompanied by an increase in volume. So, the slope of this line, whether it is here, they are positive. Now, what happens in this case? It is possible to use this concept of free energy to derive a relationship which will define, which will say what is the effect of pressure on the freezing point of water or for any metal. And this is shown over here. If we equate, say if we go back, if we equate the two, and because both are equal at freezing point. So, if you can equate the two and little bit of algebraic simplification, you will be able to show that this is equal to delta dP dt equal to delta S, that is change in entropy over change in volume. And you can multiply both numerator and denominator by the freezing temperature or melting point in degree Kelvin, that is T times T, and this is an energy which is enthalpy. that is the enthalpy, that is you can say this is the latent heat of transformation. Now, in case of this reaction water to ice, here when this from water you get ice, you have to extract heat. So, that means enthalpy is negative, and we also know that this is when ice forms, it is associated, there is an associated expansion, volume expansion. So, delta V is greater than 0. So, therefore, this is positive, this is negative, this slope is negative. So, in any cases, such cases wherever there is a reverse transformation change in volume, then the slope will be negative. Now, let us look at this, extend this concept to a very commonly used metal, that is iron. Commonly metallic material definitely is steel, which is an alloy of iron and carbon, and let us look at the phase diagram of pure iron. Now, pure iron can exist in solid state in can have different crystal structures. For example, at low temperature its crystal structure is body centered cubic, whereas at intermediate temperature its crystal structure is face centered cubic, and before melting again it gets transformed into a body centered cubic structure. So, therefore, in this particular case we expect there are several not just 3 phases, there are more than several phases are possible, at least 2 additional phases are possible, and how does these equilibrium line will be represented in the phase diagram, which is shown here. And this I have just reversed it basically, as you can do it anyway. So, I put the temperature. As an engineer, very often it is easy to visualize it like this. We will as we go later part, we look at multi component system, we will always represent temperature along y axis, and here this axis represents pressure. Now, at higher temperature, this is the region which is gas phase or vapor phase of iron, and depending on the temperature it can exist, as I said, at a low temperature it is a BCC form of iron, and it is commonly known as alpha iron. At intermediate temperature between 910 to 1400, iron has a crystal structure, a crystal structure is body centered cubic. At 1400 it again transforms, I think there is a mistake here, please correct, this is face centered cubic, and again here it gets transformed into a body centered cubic, and finally at the melting point 1539 there is a it transforms into liquid. So, you have 2 additional lines. Although I have drawn it exactly it's a perfect horizontal, there will be some amount of pressure depending on the volume change which are associated. I leave it to you to find out. See here, when BCC changes to FCC, there is an increase in volume. So, a decrease in volume, FCC is much more close packed, there is a decrease in volume. So, by heating you have a decrease in volume, and try to find out what will be the slope, it will be positive or negative. Similarly, here later on it again transforms from FCC to BCC. So, this will be associated with expansion. This is here there is a contraction, here there is expansion, and here obviously from solid to liquid there is expansion. But nevertheless, this volume change is very small. So, therefore, I have that even if there is a some definite finite slope, it will be slope will be very small. And from this it is easy to draw the cooling curve. Cooling curve will look like this. You will have, so one step here when the liquid transforms to delta, again there will be this is a solid state transformation. Here the two phases at this temperature delta and gamma can coexist. Then again at 910 gamma and alpha, the transformation gamma to alpha, FCC to BCC transformation is taking place. Here also this is a fixed temperature where both these phases can coexist. Now, let us look at the concept of surface energy. What was mentioned that for solidification to proceed, some amount of undercooling is a must. Now, is it possible to make some rough estimate what is the order of the undercooling and how does it depend on the magnitude of surface energy? And this is shown pictorially over here. Suppose in a liquid, a nucleus of solid forms. We have, for simplicity, we have assumed that it has a shape of a sphere, a spherical nucleus. Later on we will see this is the most stable phase, because this will have sphere has the minimum energy, and this is a situation is this solid, this type of nucleation, it is called homogeneous nucleation. There is no substrate, it is forming inside the liquid, and suppose it has a radius r. Then a new area is created, and area, surface area is equal to of a sphere is 4 pi r square. Now, if its sigma is the surface energy per unit area, then we can say that energy, that is 4 pi r square times sigma, this is the energy which need to be supplied for making this nucleus stable, and this will come from the transformation of the chemical free energy that gives free energy, and pictorially it is shown here. So, this is the melting point, and here definitely no nucleation, no nucleus is stable, but if you undercool here, you have this is the difference in free energy, and let us say that delta F b, this is the free energy per unit volume which it can provide, and this times the volume of the sphere, this is the net energy which this chemical reaction can provide. And for stable nucleus to be stable, this transformation, this energy should be negative, and which is a possibility. So, that means this clearly shows thermodynamically that undercooling is necessary for the nucleus to be stable. Now, let us look at and try and find out what is the concept of critical nucleus size. Now, this is the expression for the total energy that is of transformation, and this is a strong function of the dimension of the nucleus. So, this part proportional to r cube, and the second part is proportional to r square, and which is shown here. This is the surface energy increases like this, whereas this free energy per unit volume is decreases, and since the power is cube, it decreases much more rapidly. So, there is a possibility that total, if you find out, if you add this and this will show a behavior like this. And what we say that if this energy hump, there is a peak energy, if this can be crossed, then what happens that if the nucleus radius increases, the energy will keep dropping. So, therefore, this process will be spontaneous. So, for that nucleus to be stable and grow spontaneously, this energy hump must be exceeded, and this can easily be found out by finding at what size of the nucleus this free energy change is maximum. So, you differentiate this with respect to r, so and then equate it to 0. In that case, you get the critical nucleus size to be twice sigma over delta FV, that is free energy per unit volume. And you can substitute this back into this, you get what is the magnitude of this energy hump. So, this shows that higher the supercooling, the smaller is the critical nucleus size, and also higher the supercooling, the height of this energy hump is lower. So, in a way you can say that if the supercooling is more, the reaction will be much more spontaneous, it can take place easily, and so therefore, to get a finer grain size in the solidified material, you have to cool it fast, so that there is a higher degree of undercooling and the critical nucleus size is small. Other extreme, if you want to grow a single crystal, a very large crystal, then you have to use, you have to form a very low and controlled supercooling, so that the critical size is large, and then it is possible to grow large single crystal. Now, it is also possible to extend this concept to find out the rate of nucleation and how that homogeneous nucleation. Here the nucleus that has formed, it has formed within the liquid, not on any surface. So, therefore, this type of nucleation we say it is a homogeneous nucleation. And nucleation rate, it is easily, you can use this reaction rate theory, rate at which that nucleation takes place. This is a frequency term, which is kT is that Boltzmann, that energy, you divide by Planck's constant, this is the frequency factor, and this is the total frequency factor, but successful frequency of formation of number of nuclei. Out of this is the total number of attempts being made. This is then how many of this are becoming stable, that will depend on whether this can cover exceed or overcome the energy hump. This is given by that Boltzmann statistics. You say that E is the energy of transformation over kT. So, here this energy of transformation means you go back to the previous, what you can see, you can substitute this over there. So, in this expression, all these are in molar quantity. So, what you do to find out this energy, you multiply the numerator and denominator by V square, which is the molar volume, and then you get this is the molar free energy of transformation. And so, basically you can see that it more clearly says that lower the activation hill, higher is the nucleation rate and finer is the structure. Now, apart from, say, this pictorially shows, say, some nucleus has formed, but this is a concurrent process. Nucleation and growth both take place simultaneously, and this will keep growing, and then finally, when each grain it meets another grain. So, this growth in this direction is inhibited, and what finally you will get a number of grains, and each grain may have different orientation, and which is shown by different color. And this is a typical microstructure of a solid pure metal. You will have several grains, they are all differently oriented, and what looking at the microstructure, important parameter that you can find out is the grain size, the diameter of the grain, size, shape. You can also try and find out what is the average number of boundary per unit per grain. An average number, as we will go down at the end of the lecture, you will see, I will leave this as an exercise, that if you look at microstructure, this will be some number between 5 and 6. And now, you can extend this orientation of this grain. If you try and represent on a standard projection, what will happen? So, let us try to put this orientation, that cube axis of each of these grains, where they will be located. Now, if it is a single grain, say we can say that okay, one cube axis is here, 0 0 1 is here, 1 0 0 is here, 0 1 1 0 0 1 is here, but you have several of these. For the second one, it may not be at these 3 points, but maybe somewhere here, here, here. Similarly, for this it will be at a different place. So, on the whole, what you can say that these cube poles, they will be uniformly distributed as shown here with the dots. I am sorry, these dots are too fine, I should have made it little bolder. So, basically they will be uniformly distributed, whereas if there is a preferred orientation, somehow you can control the solidification, that is it is forming almost a directionally solidified structure, then possible that all cube may be located here, along this, along this, along this. So, you will have more density of such poles in these areas, whereas this portions will be vacant, there will be no dots, no poles pointed over here. Now, let us look at this heterogeneous and homogeneous nucleation. Now, in case of this heterogeneous and homogeneous, we talked about this homogeneous nucleation. In this case, the nucleus shape is spherical, it takes place within the liquid and there is a distinct interface between solid and liquid, and there is no substrate here. Suppose we put a substrate, then on depending on the nature of the substrate, if a solid forms, you will have the surface energy interactions. So, surface energy or this, as we said, that sigma is the surface energy between liquid and solid. So, suppose here this is the solid and surrounding is the liquid. So, this is sigma, and this subtends an angle with respect to the substrate theta. Now, if you and similarly there will be a separate surface energy between substrate and solid, substrate and solid, also substrate and liquid. And in fact, if you can resolve these forces should balance, that is sigma cos theta plus this surface energy between this substrate and liquid. This should be equal to the surface energy between the substrate and solid, because solid it is forming here, which is acting in the opposite direction. And usually whenever you have this kind of shape, that angle, in that case you can say that this solid, this liquid wets this substrate, and here a stable nucleus can form. So, it will depend on the surface, it will be determined by the surface energy or particularly this contact angles. And if it is wettable, then the substrate is a favorable site for nucleation of solid, and this is schematically shown. Say homogeneous nucleation, here I have tried to show there is no wall, no interface. So, within the liquid, which is in fact very difficult to reproduce and to carry out this experiment, whereas here if you allow the metal to solidify in a container. So, there is interface, solid interface available here, and nucleation will start from this end, all these interfaces. So, that means heterogeneous nucleation needs less chemical potential, the driving force for heterogeneous nucleation will be low, but it will depend on whether you have a favorable substrate or not. Now, a few points about the directional concept of directional solidification. When you allow a metal to solidify in a container, so the external cooling setup will determine how the structure or evolution of structure takes place in this solid, and this is schematically shown here in this diagram. So, you have a container, and let us say we can extract heat from one surface only. So, this is the solid part of the solid which has formed, this is the liquid, and heat can flow only along this. And as we know that when solidification takes place, heat has to be extracted. Now, in this particular case, this side and heat can flow only if there is a favorable temperature gradient. Like in the solid, here at that solid liquid interface, the temperature is the melting point. Here this is the temperature. Outside you can control the temperature. This is at your control, and you can control the heat extraction rate. So, this temperature gradient will determine that heat extraction rate, and therefore, the movement of that solid liquid interface will depend on how fast that heat can be extracted and flow through this growing solid layer. And since that, and in this case, and the liquid basically is the melting point. So, basically this liquid, some amount of heat when it comes out, if it goes here. So, basically what you will find, the temperature within the liquid, it goes up. So, if this kind of temperature gradient is maintained, in that case this, and we have seen that solid liquid surface has a definite surface energy, and it will always try to remain in the minimum state of energy. So, therefore, it is going to be straight. So, basically it is a stable interface, a planar front which will move in this direction, and this in fact, because the heat is being extracted directionally, crystal will grow in this direction. By this it is possible to grow even single, by controlling this directional solidification, it is possible to grow single crystals. Now, let us look at the structure of this metal structure a little more detail. Let us look at that how the grains, when you arrange, the what way do they pack, what is their shape, and what is the role of surface energy. Now, let us look at a 2D structure, 2-dimensional grain structure. Say suppose we draw like this, say a hexagonal grain. By constructing this hexagon, you can fill up the space. Now, point is, you can fill up the space by arranging square also, but which will represent a proper microstructure. Now, here we have seen this boundary has some energy associated. Each of these boundary has some energy associated, which is called surface tension. So, there has to be an equilibrium between the energy, which is shown here. This is the grain 1, sigma, sigma. I am putting it sigma because it is pure metal, and the surface energy of pure metal, it is, let us say, same. So, if it is same, then this angle has to be 120 degree. So, therefore, it is not that the grain surface energy of the crystal on every surface is same, but the difference on the surface energy with respect to the orientation, the magnitude of this difference possibly is very small. So, therefore, whenever you look at it a 2D structure, simplest experiment to do is with a soap bubble. If you take a ring, put it in a soap water, take it out, you will find that soap bubble which forms, that is a 2D structure, they all will be like regular hexagon, and it maintains this equilibrium. So, depending if these grain boundaries energies are little different, sigma 1, sigma 2, sigma 3, then this will be slightly different, but these angles still will maintain, I mean that equilibrium will still be maintained. Say it may be slightly less this angle, this may be slightly more, but the forces must balance. Now, what happens in case of a 3-dimensional structure, because metals, the grains are arranged at random, and that packing, when you start packing, it should fill up the space. Now, the best way to, I mean, people have done lot of experiments and making models, have tried to fill up, and the best way to fill up space is look at a octahedron. So, which has 8 faces, which is shown here. So, on the top surface 1, 2, 3, 4. So, this is 4 surface, 4 at the bottom, but this, if you try to pack, you will not be able to fill up the space. Now, there are 2 criteria, one is the space filling and second is the equilibrium of that surface energy or surface tension equilibrium must be maintained. Now, when these surfaces they meet, there will be a grain boundary, and now in 3D, say it's quite likely that many places you will have one this, one this, one this. So, there will be 4 points, like if you try and recollect that carbon, that bond structure in the 4 dimension, if all these energies are nearly equal, the angles have to be equal, and I think we said that this angle is around 109 degree or something. So, to maintain, I mean, both these, it should be a shape of the grain should be such that it should fill up the space, at the same time wherever these grains are meeting each other, there will be these lines formed, and you will have this, wherever these 4 lines are meeting, they should be at an angle around this. To satisfy this condition, it has been found that the nearest it can do is a truncated octahedron. So, this is a octahedron and you truncate it like this. Similarly, this you truncate, then you get a shape, say something, I mean, I tried to show it here, and this will have how many 8, and then it has 1, 2, 3, 4, 5, 6 corners. So, 6 more faces will be added. So, 8 plus 6. So, it will have 14 faces. So, this kind of truncated octahedron if you pack, which will nearly satisfy both these conditions, that means space filling and balancing of the surface energy. And it will be interesting to also look at this array a little carefully, the 2D array if you try and fill up. And here is an example shown here. I have tried to put several polygon, each touching each other. So, this is a space filling 2D diagram, space filling 2D array. Now, some have 5 faces, one has 6, another 4 over here. Now, when you pack them, you generate number of edges, they meet each other. This is called grain boundary. They meet each other. So, this will have one crystal arrangement, say here these planes are arranged like this. So, here possibly the planes are arranged in a different way. So, if you move from one grain to the another, the periodic array, crystal structure is still same, but its orientation is different. The same planes are oriented differently. Now, you can count, there are 3, I mean, when you do this packing, you also generate, apart from edges, number of corners where 3 or more than 3 grains meet, like here the 3 grains are meeting. Similarly, there may be places here, there are 1, 2, 3, 4 grains are meeting. So, you generate, so in this figure you have a number of polygon, that is P, you have a certain number of edges E, and you also have certain number of corner. and there is a relationship. If this is a space filling, there is a relationship like this, which is looks like similar to that Gibbs phase rule, that is P minus E plus C equal to 1. So, this is true in a 2-dimensional case, 2D case. Now, in this particular case, you try and count. So, now you have number of this grain, this is 1, 2, 3, 4, 5. So, number of polygon is 5. Number of edges I have tried to mark here 1, 2, 3, 4, 5, 6. So, you go on marking. So, it comes out to be the last one is 19. So, this is 19. So, if you substitute here, what you get is that C is 15. So, that means you should have 15 corner. Now, you count the corner, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, you get that 15 corner. So, this is satisfied in a 2D array, and this rule is quite general. In fact, there is an Euler law which is valid on surface of polyhedron, like let us say truncated octahedron we talked about. The truncated octahedron also you can apply this law P minus E plus C, but this will be equal to 2. Here also in this polyhedron also you will have number of faces, corner and edges. So, therefore, this can be applicable, it is a very general, this type of law is very general, it can be applied to polyhedron and also. Now, let us talk about the grain boundary a little more. So, we said that here is one grain, here is another grain. So, what is the atomic arrangement along this interface called grain boundary? So, this is a boundary, and I said that here crystal structure of this and this they are exactly same. So, what you do, say suppose we generate an array, the atomic array, how does it look? You can do it as an exercise, and on a piece of paper, if it you can take a transparent sheet and draw this atomic array at a regular interval. Maybe you take that closed back plane, you draw this closed back plane like atomic array, one sheet, and you repeat, you take a Xerox copy of that on another another sheet, and now on that transparent sheet you put on that and try and rotate through certain angle. And that means what you are doing, you are trying to visualize what is the nature of array near the grain boundary. So, maybe part of it you say this, that means you can you generate this atomic array by rotating this grain. So, this kind of a planar arrangement which is shown over here, it is called a coincidence lattice concept. I have drawn the same thing, this is one grain where these atoms are arranged like this, whereas in this grain the atoms are arranged in this fashion, the same plane, but it is a differently, it is rotated. Now, what happens at the grain boundary, near the grain boundary, few layer, 2 or 3 layer, what happens? So, this is the layer, this is the one grain, this is the other grain, and you can say this is the grain boundary. If you extend the lattice, you will find that some of these points, they are coincident with the lattice with these lattice points. So, which are marked over here. So, this is a concept which represents the type of the grain boundary. The nature of grain boundary people try to say on the degree of rotation and the coincidence lattice type of relationship. So, this is I mean it is not that these atoms are occupying this space, you just superimpose and see what are their coincident lattice site, and what you can find out, this coincident lattice distance, this is much significantly larger than this atomic distance. Like in this particular case, you see that here this is one atomic distance. So, here it covers the distance, this distance is 1, 2, 3. So, that means this coincident lattice dimension is 3 times the main lattice dimensions, and by this it is possible to relate and find out the surface energy or energy of the grain boundary, and this energy has a relationship between this angular rotation between to the neighboring grain, and that is how the grain boundary energies are classified. And subsequently, as we go down, you will find that it is a very convenient way of classifying grain boundary. With this, we conclude today's lecture, and in fact, we have covered this fully, this topic fully. We have talked, and next class we will begin a new chapter. Thank you very much.